Let's just jump right into it. Picture this. You're cruising down the highway at 70 miles an hour in a modern car. Right beneath that sleek dashboard and the leather seats, there's a massive, hidden, high-speed digital highway operating completely in the background. It connects your brakes, your engine, your airbags, the steering, everything. But here's the terrifying reality of complex engineering. What actually happens if just one single microchip, one tiny node on this massive network, crashes or just goes completely rogue? Why doesn't the whole car just suddenly shut down?
Well, that brings us to the absolute core mystery of today's explainer. How does a network of constantly communicating microcontrollers, a system where literally thousands of messages are flying back and forth every single second, how does it effectively police itself? How does it instantly prevent a catastrophic system-wide failure if one node starts acting up?
This glowing X-ray of a car perfectly captures the environment we're talking about here. I want you to picture the CAN bus, the controller area network, as this bustling, high-speed physical highway inside the vehicle. On this highway, the data frames are the cars, and the microcontrollers or nodes are the on-ramps. But check this out. There are absolutely no traffic lights. None. Instead, these nodes constantly monitor each other, perfectly orchestrating communication to make sure traffic flows flawlessly. If one node starts driving erratically, the system absolutely needs a fail-safe way to pull it over before it causes a massive 10-car pileup.
So, here's our roadmap for this explainer. 1. The rogue node problem. 2. Overload frames, buying time. 3. The 3 error states. 4. Tracking mistakes, error counters. 5. The acknowledgement mechanism. And finally, 6. Bulletproof network design.
Section 2. Overload frames, buying time.
Let's look past the surface and dive straight into the network's timing protocol. What happens when a node isn't actually broken, but just needs a brief moment to catch its breath? Enter the overload frame. By definition, an overload frame is a specialized signal consisting of exactly 6 dominant bits, sent by a node to delay the next transmission. Think of a dominant bit like a physical force, high pressure overriding low pressure on the electrical lines. For our visual analogy, imagine a really busy intersection. A node that's processing way too much data acts exactly like a traffic cop who briefly steps into the intersection and holds up a giant stop sign. This forces all the other traffic to halt for just a tiny fraction of a second, clearing the congestion so the node can finish its current task.
Now, the precise timing here is absolutely crucial. Notice the interframe space. That's a gap of 3 recessive or passive bits between messages. But if a node needs more time, it just blasts out those 6 dominant bits right after the previous frame ends. This forces all the other nodes to recognize the delay, causing them to also send an overload flag. Ultimately, this buys our overwhelmed node at least 15 extra bits of crucial processing time. It's a completely penalty-free way to safely buy time on the bus.
Section 3. The 3 error states. But what if a node isn't just a little slow? Let's move from temporary delays into the atomic core concept of this explainer, the strict 3-strike system that handles actual communication breakdowns. Every single CAN controller always operates in one of 3 distinct error states. I really want you to anchor this concept using a real-world analogy, a driver's license. First, we have error active. This means the node is fully licensed. It has the complete right-of-way to actively flag errors and communicate freely. Second, if it makes too many mistakes, it drops to error passive. Think of this as being put on probation. It can still communicate, sure, but its rights to signal errors are severely restricted. Finally, if the node just completely loses its mind, it hits bus off. Its driver's license is entirely revoked, and it is physically kicked off the highway.
Let's trace this out on the state machine diagram directly from our engineering source. Notice exactly how a node transitions between these states. Every node starts fully functional, right up there at the top left, in the error active state. The transitions you see pointing to the right, moving to error passive and then eventually bus off, are triggered strictly by an internal tally of mistakes. And those arrows pointing back to the left, those show the path to recovery, assuming the node can prove it's behaving correctly again. But how exactly does it calculate these transitions? Let's break down the math.
Section 4. Tracking mistakes, error counters.
To translate these abstract system states into concrete engineering logic, we have to look directly at the internal mathematics. Every single node maintains 2 distinct variables, the receive error count, or REC, and the transmit error count, or TEC. And here is our first critical mathematical threshold, 127. The equation here is simple, but it is absolute. If either the receive error count strictly exceeds 127 or the transmit error count strictly exceeds 127, the node is immediately demoted to the error passive state. And if we look at the math, adding to these counters happens really quickly. For example, adding 8 to its counter for a specific error means hitting 127 happens in just 16 rapid-fire mistakes. In this probationary state, the node can only send passive error flags, meaning it literally loses the physical power to interrupt the network.
And that brings us to the ultimate red card limit, 255. The mathematical rule states that if the transmit error count becomes strictly greater than 255, the node's output driver is completely shut off. It's forced into the bus off state. It is physically disconnected from transmitting on the bus. No way around it. But you might be wondering, why just the transmit error count?
That is a great question. The crucial point here is understanding why the rec and tech behave differently under the hood. The receive error count increases when a node sees corrupted frames, right? But the transmit error count increases when a node fails to push its own message onto the bus. The mathematical penalty for transmission errors is much, much harsher. Why? Because a faulty receiver only hurts itself, but a faulty transmitter, what we call a babbling idiot node, could jam the entire network highway. By punishing the transmitter more severely, the math ensures we quickly isolate a rogue node before it brings the whole car to a halt.
But hey, engineering isn't just about punishment, it's about recovery. Once a node is in bus off, its mathematical road to recovery is highly specific. After a host reset, the node must patiently observe the bus and successfully count 128 occurrences of 11 consecutive recessive bits. Physically, 11 recessive bits equal the exact idle time between two frames. So the equation tells us the node must silently watch 128 successful, error-free messages pass by before it is trusted to transmit a single bit again. That's a lot of waiting, but it proves the node is healthy.
Section: The Gotcha, Identical Twins of the Bus.
Before we move on, I really want to highlight a common pitfall that trips up a lot of engineers: the extreme visual similarity between overload frames and error frames. If you were looking at an oscilloscope, an overload frame and an active error frame look absolutely identical. They both consist of exactly 6 dominant bits. That's the physical structure. But here is the gotcha: their timing and their mathematical impact are completely different. An overload frame happens between frames, during the interframe space, and crucially, it does not increase those TEC or REC error counters. It's a free pass. An error frame, however, destroys a frame during transmission, and it heavily penalizes the node by driving up the mathematical error counters we just broke down. So, same exact look, totally different consequences.
Section 5. The Acknowledgement Mechanism.
We know how a node gets punished for errors, but how does it actually mathematically confirm that a message was received flawlessly in the first place? Well, the answer lies right here in the acknowledgement mechanism. Look at the specific timing slot highlighted here, the ACK slot. The sending node always transmits a recessive bit in this exact slot. A recessive bit is weak, but every single node on the network that successfully receives the frame without errors will simultaneously transmit a dominant bit in this exact same slot. Because dominant completely overwrites recessive, the sender mathematically reads back a dominant bit. This creates a brilliant, instantaneous positive confirmation from the entire network cluster, all without needing an entirely separate reply message. It is remarkably efficient.
Section 6. Bulletproof Network Design.
We've covered a tremendous amount of ground today, moving from the physical bits on the wire all the way up to the mathematical thresholds that keep the network alive. Let's summarize the most critical engineering takeaways for this fail-safe architecture. First, remember our traffic cop. Overload frames use 6 dominant bits to safely buy processing time without any mathematical penalty. Second, the 3-strike system. Nodes escalate through active, passive, and bus-off states based on strict mathematical limits, specifically the 127 and 255 thresholds. And finally, the transmit and receive error counters are explicitly designed to harshly isolate a rogue, babbling node, completely cutting off its output driver to protect the rest of the automotive cluster.
Understanding these protocols isn't just about passing a test. It is the exact practical intuition required to design vehicles that are fundamentally safe, even when the silicon fails. You are now equipped with the mathematical and logical rules to understand exactly how cars survive network crashes. Hit subscribe for more EMC and automotive communication protocol survival guides, because honestly, if engineers can make a chaotic, light-speed network of microchips perfectly self-healing, what other complex systems in our world could we fix with just a little bit of bulletproof logic? Keep engineering the future, and I'll catch you in the next one.